Okay, so in this video, I'll be going over the measurements of all the two-dimensional shapes that we have covered so far, including the circle, which will come at the end, because the circle has a little bit of a complex measurements method. But I'm going to be going over how do we derive or obtain these certain measurement formula. So I'm not going to make it such a long video. I actually want to try and run through these, right? But also try and keep it at a certain pace where you can actually follow. So the first one we're going to be dealing with is a square, right? So a square over here, this does not look like a square, but let's just call it a square for now. Then we have our other square here. This looks more like a square. Okay, so for these squares over here, what we can see is we want to work with the perimeter, right? We want to get the perimeter. Now, how do we get the perimeter? The perimeter would normally be all of the sides added together. We want to cover the total amount of the total measurement of the outside of the shape in this case, and it would be this side plus this side plus this side plus this side over here, and we would call that side 1, 2, 3, and 4. So the perimeter of the square would just be equal to side 1, so I'll just call it 1 plus 2, or we can just call it sides because we have all of these sides equal in length. So it'll be side plus side plus side plus side, and because all of these sides are equal in length, we can say that all of these are like terms in this case, right? We treat it as variables because we don't know them. So because they're unknown to us, we can call them variables, and s plus s plus s plus s is just 4s. And because it looks like a 5, I would normally just draw an s over here with brackets. Okay, and that is normally what the perimeter is going to be. I know the perimeter is actually just going to be adding all the exterior sides together, basically. That's literally all that we're going to do with the perimeter. But let's move on to the area, right? So the area is going to be, okay, so let's actually look at these dimensions here, right? Because we have a two-dimensional object, we are going to be looking at only 2 dimensions, right? 2 dimensions, that's how you spell dimensions. Okay, but what we are going to be doing is we are going to multiply the 2 dimensions together. So if we were to have the side over here, because they're all equal in length, all of these sides, because it's a square, we can see that this side is also going to be represented as side over here. So because we are going to be multiplying the 2 dimensions together, we are going to get the following. It's going to be the area of a square is equal to side times side, which is equal to side square. As you know over here, according to exponent laws, or you just know that something multiplied by itself once will just give you square or exponent of 2. And as you can see, we name this thing square over here. To the power of 2 is normally represented as square because we have a square over here. That is mainly where it comes from. And we have 2 dimensions. And you'll see when we cover 3-dimensional objects, if we have a 3-dimensional object over here, right, our amazing 3-dimensional object, where we would have, let's say, for example, the side here, multiplied by the side over here, these 3 dimensions, if you multiply all of them together, you will have something. So let's just say, side cube, side to the power of 3, or it can be represented side times side times side, and that's where this cube comes from. Because we were working on a cube, and this was a cube, by the way, now we actually say to the power of 3, and that's where we actually got this cube from, because whenever we work with a cube or a square, we would normally get these numbers as an outcome when we were working with variables, certain variables, or our unit of measurements, if we have like centimeters square or square centimeters, or even centimeters cube or cubic centimeters. And that is where those exponents actually come from, and their names come from in that case. Okay, let's move on to the rectangle, and then at least I'll get into more detail with the area for the for why do we find the area, basically. That will be the most detail for this video, hopefully. Here's our next shape that we're going to be dealing with. So with this shape over here, it's a rectangle. And what do we know about the properties of a rectangle? The properties of a rectangle is that opposite pairs of sides are equal in length. So 2 opposite pairs of sides are equal in length. So let's look at our dimensions over here, right? We have this one. We normally prefer the longer side to be represented as L, which is represented as length, right? And then our other side, which is going to be here, would normally be the breadth, which is represented as breadth. Or you could say width, which is represented by W, or you could say D, which is represented by depth. But normally we don't use the D, so we normally use these two over here. But you could use either one. So with the perimeter, I said we're going to add all the sides together. So let's just call this B for now, because most teachers would use this one, and this would be the length because of these equal sides here. Those are where the variables come from. So if we're looking at the perimeter of this rectangle, we would have the perimeter of the rectangle equals to the length plus the breadth plus the breadth, which is basically all of the sides added together. And we have like terms here. We have L and L, and we have B and B. So it's 2L plus 2B. And if you wanted to write this into more detail here, you could take the 2 out as a common factor, and then you have 2 multiplied by length plus breadth over here. And that's in some textbooks, and some teachers would normally go over this, and sometimes it would look confusing. But once again, it's only taking out common factors. It's nothing too hectic. But once again, you don't really need to use this. We don't normally use it. We normally use either this one, which is probably our simple one, and it also correlates to our volume formula for our total surface area for a 3-dimensional cuboid or rectangular prism. But let's not go there right now. We're on 2-dimensional objects. So we dealt with the perimeter now. Now, how do we find the area? So let's look at these dimensions, right? We have the length, and then we have the breadth, right? And let's just actually give it numbers. Let's actually use numbers. Let's say this is 3 meters, and then let's say that the breadth over here is equal to 2 centimeters. Not centimeters, sorry. Let's not make it that complicated. Let's use the same unit of measurement. Now, because we named this length 3 meters, we need to represent it as according to its we need to use lines that are parallel to this length in our case over here. And remember, we know over here that this side is going to be equal to that side. This side is going to be equal to its opposite side over here. So what I'm trying to say is we need to have 3 rows and 2 columns, right? So the length would be the rows. So let's just do that. So we have this, and we have this. And as you can see, there's 1, 2, 3 rows in this case, represented by the length. And then for the breadth, we will have 2 rows in our case over here. So that would be just splitting it in half in this case over here. So because of that, we have 1, 2, 3, 4, 5, 6 blocks, right? And that is actually represented by the area within this shape. And that is how we find the area. And let's just do that, right? Let's actually use the area formula to solve it, right? The area of a rectangle is going to be equal to the multiplication of the two dimensions, which is the length multiplied by the breadth, which is just going to be equal to 3 meters multiplied by our 2 meters, which we get 3 times 2, which is equal to 6. And the reason why I kept the meters in over here is because if we multiply the meters together, we will get meters square in our case over here. And as you can see, this 6 is basically the same as this. Remember, there's 6 little blocks inside of this rectangle that we have created, remember, according to our rows and columns that we have made to form a certain amount of blocks. And that is what area is actually telling us. And the reason why we have an area formula is because sometimes there could be maybe 1,200 blocks or 2 million blocks. I don't know how you get to that point. But that is exactly why we use the area formula, because it does get hectic and we are not counting 1 million blocks, which is a lot of blocks. So that's why we have calculators now, or we have mental math, which I recommend using, because calculators are just, yeah, shame on you. But yes, that is why we have the area formula, instead of just counting a whole bunch of blocks. Let's move on to the next shape, which is a student favorite. So now we are dealing with the perimeter and area of a triangle. Okay, so as you can see, we have three shapes here, but let's not focus on the area for now. Let's just quickly do the perimeter. Like I said, we're just going to add all of the sides together. So it's going to be this, plus this, which will basically give our area, sorry, not our perimeter of the triangle, which is going to be equal to the sum of all sides. I apologize for using sigma right now, but right now I'm just going to say the sum, or let me just say the sum of all sides. That is what sigma means, the sum. I apologize for my usage of it. I see it way too much in my field of academics. So right now, that's just what a perimeter is. You just add all the exterior sides. There's nothing too hectic about it. Let me just move on to the area, because I don't want to stress the perimeter too much, because I don't normally ask the perimeter questions. But still, be prepared, please. Now the area, let's actually get there, right? So where on earth do we get this formula from? I know that you've seen that the area of a triangle is equal to a half times the base times the height. Now where on earth do we get this from? Now that is a really good question here. So as we can see, right, let's say for example that this is our right angle triangle, right? And let me just make this a little bit more thinner over here. What we can do is, let's just look at our let's look at it as if it was a rectangle over here, right? Where we would have this as the length and this is the base, right? Oh, sorry, the breadth. Now, as you can see with our rectangle, I know it's not the best looking rectangle right now, but let's just say it is a rectangle, right? And we have length times the breadth. And we can see this line over here as a random diagonal that cuts the rectangle into two triangles, where you can see that this triangle is a triangle, a right angle triangle, and this over here is also a right angle triangle, right? So what we are actually doing, in order to get this half, we are gonna half that that rectangle by putting a diagonal to cut it in half. So, and then we get rid of that other triangle that we had, and we will be left with this, right? But we only have one dimension over here. We need to actually specify certain dimensions. So we actually working with something different this time. We are working with height over here, the height of a triangle, how it's upright, and we have over here the area, oh sorry, not the area, the other dimension, which will be the base. I know the base and the breadth are not really the same thing, but the base would be like where the triangle lies on, basically. The bottom of the triangle normally. And the height would be an upright measurement, normally perpendicular. So note how I'm going to call this the perpendicular height, because you can see this right angle over here. We can actually do the measurement. And that is where the half comes from. We are halving a rectangle, and then what we are actually going to be doing is we change up the dimensions, the dimensional names from length times breadth to base times perpendicular height. Normally I would recommend saying perpendicular height, so say perpendicular height. Okay, that one is simple, but look at this one over here. We have a triangle, and in measurements, we don't normally like to work out a diagonal line, right? We normally like to work out straight lines. So let's do this, right? How do we do this? Let's start off over here, right? The base of the triangle is represented by B over here, right? That's the bottom of the triangle. So we know that that is a nice straight line that we have in front of our eyes over here. And the rest of the sides are actually diagonal. So what we are going to be doing, in order to get a nice straight line over here that is not diagonal, what we are going to be doing is we need to draw a line from the apex of the triangle or the vertex of the triangle, such that this new line that we've constructed is perpendicular to the base. And that is exactly why we call it also, once again, the perpendicular height when we are working with triangles. Because we have a perpendicular sign over here, a perpendicular geometrical symbol. That's what you can also call it if you want to be fancy. And once again, that is what's represented here by this right angle triangle. Now you can see that we have one right angle triangle and we have a second right angle triangle. And in our measurements, we don't use this, we don't use those certain bases over here. Like let's say we created a new height like that, right? So therefore, should we actually represent this as our new base? That's probably your question. No, you don't do that. You work with the same base that you were given initially of that same triangle. What you did was just to create a new perpendicular height so that you can actually get the measurement and use this formula over here. So let's say, for example, that our perpendicular height over here is going to be equal to, let's say, 5 meters. And then this breadth over here is just going to be equal to 3 meters, right? And then what we are going to be doing in the formula, we're going to say that the area of a triangle is equal to a half multiplied by 5 meters multiplied by the base, which is 3 meters. And we are going to get an answer of 15 over 2. We're multiplying the meters together, so it's going to be meters square. And once again, it's area. So normally we would represent area with our square. Or our exponent as raised to the power of 2, or you could also say it's equal to 7,5 meters square. Okay, that's what the triangle. Now let's move on to our next shape. All right, so I think this is one of the shapes that actually does it uses the diagonals in the area, right? But what I want to do is quickly just go over one of these formula that doesn't have the diagonal. Let's say, for example, if you don't want to, well, if you are just given like a certain question on the examination. Sorry, my words are leaving me right now. It's been a long day. Okay, so let's look at our rhombus quickly, our properties, and I'll explain to you as we go, because I think I'm confusing myself and I'm probably confusing you. We know a rhombus has all 4 sides equal in length, but obviously not all of them are parallel to each other. It's basically just a square, but it's tilted a little bit to the side. All right. So what we are going to be saying over here is that it's going to just be this side over here. So we can kind of represent it as this side over here, this side, and this side. So the perimeter of a rhombus is just going to be equal to side plus side plus side plus side, which is just going to be equal to 4 times side, or 4 side, basically. So nothing too hectic about the perimeter. Once again, it's just equal. It's just going to be the sum of all of the sides outside of the shape. Now let's get the area of the rhombus. So note that we have diagonal lines over here outside of the rhombus, right? We don't like to measure the outside diagonals of a shape, right? Normally we would find an area where we'd actually find the diagonals of the inside, right? But in our case over here, let's just do this, right? So it will only apply. Okay, let's first look at the common formula that we use for this. It's the same thing we've done with a triangle, because remember we had those diagonals. We had like 2 diagonals, and we wanted to work with straight lines, basically, right? So what we have over here is it was the base, right? And what we did with the other triangles, we created a straight line that was actually perpendicular, which we called the perpendicular height, right? And that is how we actually get the area of the rhombus. So it'll look like this. It'll be the area, that is a triangle. The area of a rhombus will be equal to the base multiplied by the perpendicular height. Notice how I didn't say a half over here, because we don't have a half into the formula. It's not like the triangle, how the triangle was derived. But there is a formula that we use for measurements where we do include a half, and it involves triangles. And what I'm going to say over here is I can't really visually represent it right now of how we get that formula. The formula goes as follows, but I will try and explain it to you. So you can use another one, which is, or the area of the rhombus is just going to be equal to a half. Now let's just create some dimensions over here, or sorry, let's create some extra lines over here. We're going to do the following. We're going to join the corners, the opposite corners together, and this opposite corner here, such that this one would be called diagonal 1. But I'm going to call it D1 for now. D1. And then this diagonal, which is not the other diagonal, will be diagonal 2. D subscript 2. Notice how, okay, I'm going to write here, diagonal, d is equal to diagonal. Okay. Now, what we are doing in this formula is we are going to take a half and we're going to multiply it by d1 and multiply it by d2. It has something to do with the certain triangles. The triangle will like flip basically, so it'll roll over, like so. Like the triangle will roll over such that we get like basically two squares. But there are videos on the internet that actually show good visual representations. So just look that up, and you'll see how you do derive it. So I will recommend you to look at visual derivations of the measurement formula. But right now we just know this formula as a half multiplied by the diagonal 1 multiplied by the diagonal 2, and that would be the area of the rhombus in our case over here. Now let's move on to the next area, because this one is not my best part when it comes to visually representing a new formula such as this one over here, because you would probably have to use nice video editing and all that stuff. But yeah, let's move on to our next shape. Okay, our parallelogram. As you can see over here from the name, I just once again, I am a mathematician, so I am lazy. I'm not afraid to tell you guys, so I did not feel like writing all of that stuff down. So over here, let's look at our I was going to say rhombus. Our parallelogram. We know that the opposite pairs of sides are equal in length, right? So this will be equal to that, that will be equal to that. And then let me just do it over here as well. And then that's equal, this is equal. Okay, not my best writing here. So what we are going to be doing over here is the perimeter. Now the perimeter of a rhombus, so let me just do, there we go. Cool. I really don't like these subscripts that I'm making, but it's fine. You could also do this in the examination, or you can actually write the actual word out, which I recommend doing, because sometimes if you draw it down, sometimes you might make a little bit of a mistake there with your shape, but it's fine, it happens. Let's just look at this, right? We know that the perimeter is just going to be the sum of all of the sides, right? So let's just call this the length, and let's just call this the breadth, right? So this is the breadth, and this is the length over here. So we're just going to add all of them together, remember. So it's the length, and this would also be the length over here. This would also be the breadth, because of their equal sides. Length plus breadth, which can be equal to 2 length plus 2 breadth, or it could also be equal to 2 into length plus breadth. So this is basically the same as the rectangle, because obviously, once again, it kind of follows the same properties as the rectangle, and that's why you need to know your properties of your shapes. So it's actually easier to derive these formula. The perimeter formulas are so straightforward. I don't even think you have to write it down. But I think some teachers would want you to write it down from how they taught you, because they like to control you guys. No, I'm just kidding. They don't. Okay, not all of them do. But yes, these are our formula, basically, for the perimeter. It's literally just the sum of all the sides. It's nothing even hectic. I don't even think you have to write the formula down. Just show them I know what I'm doing. I'm adding every single side here, and then it should be fine. All right, now let's get to our area. And remember what I said about the diagonal lines outside of the shape. We do not care about those ones. Obviously, that's not why we don't do the measurements, but what we would normally do in these cases over here is it's going to be the, sorry about that. We have the base over here of this parallelogram, and we want to find out what is the perpendicular height. Once again, this really makes our life easier whenever we are trying to find the area. And once again, if you want to look at visual proofs of how these were done, you can go for it and search it up. I have nothing against it, obviously, because I'm just trying to show all of these formula so that you guys are at least on the same page with me over here. Then we have the area of the parallelogram, which is just going to be equal to the base multiplied by the perpendicular height. And obviously I could add numbers to it, but once again, it's not really useful. I'm pretty sure I've already done some examples and showing you how it would be a square, like meters square, for example, because they multiply each other in the area. So perimeter would normally just be meters, for example, and then area would be meters square or centimeters square or whatever, or perimeter would be centimeters and whatever, any unit of measurement that you use. Okay, and then that is the area of the parallelogram. So I don't have to go into too much detail. There is no diagonal one that I can see at the moment. But yes, this is our area of the parallelogram and perimeter of the parallelogram. Let's get to our last two shapes that we have, and then our final one, which is our circle. So let's not waste too much time here. Okay, so the trapezium is a very nice one. I'm pretty sure I can visually represent on why we get these formulas. Okay, so let's do this, right? Once again, this again, okay. What I want to do over here is you're just going to add all of these together, and then this, and then you'll get your perimeter of your trapezium, and then that's just going to be the sum of all sides. So nothing too hectic about that one. Let's move on to the area. So with the area here is, okay, this is going to be a crazy one. I'm gonna try and see if I can actually explain this one very good. Okay, so what we can see over here, right? Let's say that we have, okay, so we know this rule, right? Obviously this is not going to be the same as that, right? Because you can clearly see that they are different in length. So we know that this is parallel to that, right? So now this is the part where we're using parallel lines. So let's just name these two differently. Let's call this A and let's call this B, right? So two variables in our case. The B could be represented as our breadth, or sorry, our base in this case, but A is our extra variable that we're going to be adding. So obviously it's lowercase a so that we don't confuse it with area when we name it capital. Okay, so let's do this, right? So what I'm going to be doing is I'm going to create a random, let's say, line from this point here such that it's perpendicular, right? And over here, what I'm going to be doing is I'm going to create a point here, and then I'm going to say that this is going to be going all the way to that other corner. So it's going to go from this corner here all the way to this corner here, right? So what we can see over here is we have a triangle over here, and we also have a triangle here, right? So over here, what we are going to say about this triangle here, let's say that we are going to have this triangle here. I'm going to try and draw the outline of this one here. That triangle there, it's a very nice and neat line. We can represent this by its perpendicular height over here, which is represented here. So this area of this triangle would be equal to a half the A multiplied by the perpendicular height, right? So that would be our one triangle here. If you did get confused, please just go back over here because I'm trying to break them up into triangles. Okay. And now let's look at the other triangle, right? So we have this triangle over here. Okay. And then that area of that triangle would be, let me just write it here. It would be the area equals to a half B times the perpendicular height, right? Okay, because we have B as our variable in this one here. So now let's try and derive the area of this of these together. So in order to get the area of this trapezium, we are going to have to add these two areas together, right? Because we already have the areas of the two triangles. Now we just have to add them together to get the total area, right? And this is how we derive the area of a trapezium. So let me write it like this because I've been doing it. I've been doing it the whole time. So let me do this. Okay. So the area of the trapezium is the sum of those two. So it'll be a half A times the perpendicular height. So A multiplied by the perpendicular height plus a half multiplied by B times the perpendicular height. And then over here, we just need to take out common factors, right? So a half is our common factor that we can take out. And then we have, we can also take out the perpendicular height, which you can see over here. That's exactly what we're doing. So normally your formulas would look like this actually. It'll be A plus B, which you can see over here. A and B are left over here because we took out a half and we also took out perpendicular height as common factors. And then we can see this is multiplied by the perpendicular height, which was also taken out as a common factor. You could also write it like this if you are still like kind of new to taking out common factors. If you're not really comfortable, you can also say a half multiplied by the perpendicular height into A plus B. And that is where this came from actually. It's basically just a half times the perpendicular height that you've created, which was over here. And then inside of this bracket, it's the sum of this two parallel sides over here. The only two parallel sides of the trapezium. And that is how we find the area of the trapezium. I know it's a little bit of a hectic one that we have to get. But once again, I hope that this actually helped, this visual explanation over here. Let's move on to our last actual shape, and then we move on to our final shape, which is the circle. So let's just do the kite right now. So this is another one of the shapes like the rhombus where I couldn't really point out how we get the area using visual representations. The trapezium was an easy one because I can actually show you the two triangles. But obviously I can't roll these triangles out of this stuff because that is a next level of experience. So check out how you can get the area for the kite. But let's actually go through this, right? Because that's why you're here. So once again, the perimeter, just take this side, take that side, take this side, and take that side. And then the perimeter is just of the kite is just going to be equal to the sum of all sides. Okay, sorry about that. Let me stop that. The sum of all sides. Okay, now the area. Now I want to just quickly zoom out like this so that we have more space. All right, cool. So now the area is just, let's look at our properties of the kite, right? So I'm going to just quickly do this. We have, let's just draw a nice straight line like that. Quickly, just to make it easier for us to see. So it's going to be like this. And then we have this corner going all the way to here. Okay. Okay. And then we have all of these ones are going to be perpendicular, right? Like that. And then we basically have this equal to that. And then this one is going to be equal to this one here. Two pairs of adjacent sides are equal in length. That is what our property says. So now that I have all the space, I can actually write it here. So over here, right, to get this area, the half is indicated. So the area of a kite, like that, okay, it doesn't look nice, but still, is going to be equal to half multiplied by, and over here, let's just look at it like this, right? I know that these are the outside lines, but what we have created in red is actually our diagonals. And we can call this diagonal 1, and then this diagonal here, we can call diagonal 2, where D represents diagonals. That is our key over there. So we're going to multiply the half by the diagonal 1, and then multiply that by the diagonal 2. And once again, I said, for the visual representation, sorry, let me just fix this up over here. For the visual representations, I recommend looking at videos. There are very, very great videos out there that actually show you how you can get these areas. But these are given areas that I have, because most of them I can get by actually myself, by just looking at the shape and okay, I can see these dimensions. Let me just multiply them. Let me add them together to get this certain perimeter or area, right? But some of them you need to obviously take them apart one by one. But once again, that's not going to be the point of this video. I'm not going to get into too much detail, but here is the formula of the area of the kite. Now let's get to our actual last shape, and then we can call it from there. And this shape is the circle. This is what we've all been waiting for here. So let's get into the perimeter. Now normally in this whole video, I've literally been telling you that the perimeter was like, okay, it's just side by side. This is different. Now, let's look at this circle, right? Now, what do we know about a circle? A circle has a circumference, which is this outside line right here that forms a circle, right? And now let's consider the center of a circle like this, right? And we construct our radius. And we know that the radius is actually half the diameter. So we can write this, the radius is equal to d over 2. Right? But let's not focus on that right now. So this is the radius. And the radius would normally go perfectly around the circle a certain number of times. Okay? But the radius over here is going to go from the circle center, which would normally label CC, and then here it touches the circumference of the circle. And now this radius starts at 0 degrees. Let's say that this is 0 degrees, right? And then it goes in a rotation. So let me just change the color here. It rotates from this point here all around the circle until it reaches exactly over here. It makes a full revolution, which is 360 degrees, right? So now what we are going to be doing is we are going to be looking at 360 degrees and the radius carefully. Okay. So let's look at this, right? The circumference, we're not going to call it the perimeter anymore. C is the circumference, and we need to find out what is the circumference of the circle. That would actually be the perimeter of the circle. And how do we get the perimeter? Now we have the radius, right? We are actually going to multiply this radius by the revolution that it makes to create a circle, which was 360 degrees. But we don't say r times 360 degrees, right? Whenever we do, when we were doing mathematics, we never really used degrees as an angle. Normally we'd use pi radians or just radians, where 360 degrees was just going to be equal to 2 pi radians. Or you can write it as rad, not because normally, I did write down degrees, but I just did a circle. This over here is degrees, and then this over here is just radians. But we don't work with this in high school. Most high schools don't work with radians. If there are high schools that work with radians, consider yourself lucky, because in university that is where we work. We work with radians instead of degrees in mathematics. So we're multiplying the radius by the revolution of the circle, basically. And that is where we get the c is equal to 2 pi times the radius. Now, let's look at the area of the circle. Now, the area of the circle is almost impossible to actually visually represent, but I'll try my best. So what we have over here, right, is the circle. So I'm going to draw a circle center here, and then a radius like this. And I'm going to draw another radius, which therefore this is the diameter, right? And let's say that we were drawing, if we were to take these two circles out, it would look something like this, right? We would have a semicircle here, and we would have a semicircle like this, like that. Okay, you're probably wondering, what on earth am I doing? I'm trying to get to a point where we actually get to a rectangle. So there was this video that I actually saw that actually explained how these things are derived. So let's say, for example, we have this diameter and this diameter over here, and then we have this diameter here, and then we basically just break it up into sections like this, and then it would be, this is more of a curved thing over here. So it would be like that, and then we would have something like this, and then this. We would have something like teeth shape, basically, right? And then there would basically go as a large number of these pie slices that would connect together so that we can actually get a rectangle, right? Because it would be something like this, all of them together. But there's a lot of them, and that just deleted it. Now over there, we are going to be taking the pi amount, which is basically represented by the straight line, because now what we are saying over here is that actually 180 degrees is equal to pi radian, right? We don't know, most of you don't know this, but that is what it is in radians, if you convert it. And essentially what we are doing over here, we are taking that radian, pi, and we are multiplying it by the radius, which is multiplied by r in that case. That's the one dimension of the circle over there, right? or of the rectangle, sorry, that was created, that was manipulated such that it actually makes a rectangle. And then over here we would have just the radius on its own, because this pi was made from the circle, and then the radius here was just made from the radius in that case. And then if we look at this, right, this is actually equal to the length of the rectangle, and this would be the base, and therefore the area of a circle would just be equal to the length times the okay, no, don't say that, please. The length times the breadth of this one, which is pi times r, multiplied by the breadth, which is just going to be the r, the radius, and then therefore the area of this circle is just going to be equal to pi times radius square. There's also a video on YouTube that really explains this well. I use that as reference, but it actually explains it very well. It's like a 2-minute video. It's very quick, but I tried to explain it like how we actually get these dimensions if you are interested, and that is how we get the area of a circle. So if we ever to also, just something cool to know over here, I'm just going to add this over here. If we have a semicircle, right, what we would normally say is this would actually just be the area of the semicircle would just be, remember that a semicircle is basically just half of the circle, right? So half of circle. So therefore the semicircle will be half of the area of the circle. So it'll be half, sorry, my fault. So the area of a semicircle will be half of the area of the circle, which if we substitute it in, it'll be a half multiplied by pi times radius square. And then that is how we get our formula for the semicircle, because normally they would give us a semicircle, and in the exam questions that I'm going to be going over for the 2-dimensional shapes, I will be already created my own, and I'll show you a very beautiful question on all of this. So that's the area of a semicircle. And then here, obviously, here's the area and the perimeter of this circle. And that is all the shapes that are 2-dimensional that I can go over. The next video will be on 3-dimensional objects, and that's going to be a little bit of a spicy one, but there's not too much to deal with there. But I'll probably quickly make like videos on the maybe exam questions on 2-dimensional shapes, and then the rest of it or the other videos will just be on 3-dimensional objects, which is a little bit of a more tricky one, but it's absolutely fine. It's nothing too difficult. I hope you enjoyed this video, and I will be making the next video on the exam questions.